looking at regularly parametrized models, which is basically a technical tool to calculate the RLCT of certain functions. Oh, quickly, do I want to attach to the orb as a speaker?
Yeah, that's right.
Okay, cool. That's done now. Okay, so basically a technical tool to calculate some RLCTs, but it does have a kind of appealing conceptual content which links the program synthesis or indeed statistical inference of SLT with geometry by linking each sort of model prior truth triple a to an ideal in the ring of analytic functions. Anyway, so before we do that, we're going to have to define the RLCT of an ideal, and then we prove a theorem that links the two. So a certain ideal to the function in question. Anyway, so throughout, we'll be working with some subset W of Rn, which will be compact and semi-analytic. That just means that it's cut out by just the non-negative lockers of some collection of analytic functions, and AW will be the ring of real analytic functions on W. So I'll just quickly remind everyone, I believe this would have come up when we were talking about the asymptotics of the free energy, but what I mean by the RLCT. So definition, if F and phi A are non-negative analytic on W, then we write RLCT on W of F with the prior phi will be a pair lambda theta such that so there are a few equivalent definitions, and the reference that I prefer is probably Lin's thesis, but I assume it's also in the grey book. So either we can look at this so-called partition function, Zn, which is the integral over W of e to the minus and that will have the asymptotic expansion as follows. The minus logarithm of Zn will be lambda log n minus the minus 1 log n. And so this is the sense in which we use it in SLT, because the partition function is exactly the form of the integral of the posterior over some subset W. And so this shows us that the RLCT lambda controls the asymptotics for large n. We often don't care about the log n terms, but we might as well keep it because it doesn't really change any of our analysis for the moment. So in practice, the way we actually calculate this is more often through the so-called theta function. So for a complex parameter z, theta of z is also the integral like that. So its poles are real. It extends to a meromorphic function on C. Again, these proofs are in Lin, or at least there are references there. And the smallest pole is lambda with multiplicity theta. And so this is proved by resolution of singularities, which is probably a story for another day. Yes, and so when we are, I will approve a couple of lemmas that talk about ordering these pairs, lambda and theta, and basically what that ordering comes down to is ordering these asymptotic expansions. So what I mean by that is that lambda theta will be strictly less than lambda prime theta prime if lambda strictly less than lambda prime right, does that make, is this all familiar to everyone? Is there any questions or clarifications I can make on that before I move on? Cool, well I'll jump over to the next lot of okay, so this lemma is kind of what controls a lot of these estimations we're making and the way we get bounds on the RLCT. It's a remark in the greybook where it's stated incorrectly and not proved, and then everyone just seems to point to this remark. And so anyway, we'll actually prove it. So if f and g are analytic and non-negative, and there exists a c greater than 0, so that right. So to prove this, we will look at the asymptotics of the partition functions. You can also look at the resolution of singularities if that tickles your fancy. So we can, if we look at this integral of e to the minus n f of w, then just by monotonicity, you can observe that this is going to be larger than the corresponding integral, but with cg in it. Oops. Minus cn g of w by f w, which of course is just z g of cn. We usually assume n is an integer, but it doesn't really matter in this case. Okay, so why does that help us? But if we take some logarithms and a negative, then the inequality swaps itself around. So we know that minus log zf n will be less than or equal to the minus log of zgn. So we can use our asymptotic expansions. This tells us that...
Sorry to interrupt, Tom.
Yes.
Could you either speak up a bit or maybe walk your character back towards the orb a little bit? It's actually a little hard to hear you.
No problem. Does that help?
Yeah, that's better. Cheers.
Okay, so I want to stand next to the orb is kind of how this works.
Yeah, so people who are attached to the orbs with the halos on their heads are listening from the position of the orb. Okay. So you're standing next to it, then your volume will be okay.
Gotcha. Perfect. Right. Okay. So if we're just this is just recreating the asymptotics that we had before. Lambda g log of now Cn. And then plus O1. I'm not sure if I put that in the previous one. Anyway, that's what I need. And so I won't go through all the enunciating details. They're in the notes if you're interested. But you can kind of see that the constant part of that pops out as a constant, and likewise with here, you get an extra O1 term. And so what that tells us is that if you make n big enough so that the log n dominates all the O1 terms, then lambda f log n minus, oops, will be less than or equal to lambda g log n minus theta g minus 1 log n for n. And so this exactly tells us that we have the required relationship between the RLCTs. Okay, so this, oops, no, all over the place. Is that orb in the right place now? Yes, cool. Okay, so fortunately for all of us, the actual order of the inequalities doesn't usually matter, because the way we use this result is through the following corollary, is that if we have CD greater than 0, so that CGW then the LCT and so we'll refer to this as these functions being comparable. That's Lin's term. It looks a lot like Lipschitz equivalence, so we sometimes use that term as well. Okay, and so that follows fairly directly from the previous result. So in our specific case, when we're trying to look at the RLCT of an ideal, the way we do that is by taking the sum of squares of the generators. And so that requires a choice of generators, but it ends up being well defined via this corollary here. So say we've got two ideals, F1 and J, inside the ring of analytic functions. If I is a subset of J, then the RLCT W of F1 squared plus is less than or equal to right, and so this, given that we've got an inequality, we're going to be using the lemma from earlier. And so the way that looks is, well, first, for each I, we can write it in terms of the GJ with functions for coefficients. That's just what it means for each of the Fi to be in the ideal J. So that says that Fi equals the sum J equals 1 up to R of Hij times Gj. Where each of these Hij are in this ring of analytic functions. So then by Cauchy-Schwarz. Oops, let's get the constants in the right order. That tells us that fi squared, which is just is less than or equal to the squares of these hij's times the squares of the gj's. So that's great, because then the function we're interested in, this sum of squares of the fi's, is going to be less than or equal to just all of these. That's not exactly what I want. Oh, sorry, I forgot this entirely wrong. These squares should be on the inside. That's how that works. Right, and so that makes this all work out how we want. Okay, so we've assumed that the parameter space W is compact, so this is bounded. Which gives us, so these are the functions that we're interested in the RLCT of, and so that's just, we have the sum of the fi squared less than or equal to c times the sum of the gj squared. So that proves the corollary. Right, and so again, we're not super interested in this, but what that tells us is that the following definition is well defined. Okay, back over here. So if I is some ideal, where now we're just fixing a choice of generators, then we define the RLCT on W of I with this prior to be just that sum of squares we wrote down earlier. Okay, and so obviously if we choose two different sets of generators, then we have both inclusions between the ideals, like in the previous corollary, and so the RLCTs must be equal. So just as a little note of caution, this differs from the definition in Lin, which is basically the reference for all of this stuff. And so as a result, well, you'd think I'd get that right by now. If we have a given function which has an RLCT of its own, then the RLCT of the ideal it generates might be different. Well, it will be different by a factor of 2. And so you could see that by looking at the zeta functions, because this, yeah, anyway, the square in the generator is what gives that to you. This is kind of mild because we care about the RLCTs of ideals because of the following result, and in that case it turns out we want the factor of 2, and so that's, yeah, and so this works out for us. Before I jump into proving that theorem, I'll just say a couple words about why I think looking at ideals rather than functions is kind of appealing. And so the main reason for me is that it's a bit more flexible. So if you have a fixed function, you have to, like, at each point prove that if you're modifying the function you're calculating with, that it doesn't change the ideal. So you keep proving these Lipschitz equivalents, whereas with an ideal, you will have the flexibility to choose a set of generators, and because you're in the ring of analytic functions, you kind of have a good stock of units, and so that makes choosing these generators quite easy, which, yeah, can make calculations of these ideals significantly simpler. The other point is that these ideals, this notion that we've got here of these RLCTs has some nice properties with respect to, well, so we've already seen with respect to inclusions, but if you have sums and products of ideals also kind of work nicely. And all of these, I think, become clearer looking at the ideals rather than at the functions. So if there's time after, which probably there should be, after I've proven the next theorem, then I will sketch some of those properties, but otherwise there's a link in the notes to just some little thing I've written on that. Okay, so without me continuing to speak, I'll pop onto the next board and state the theorem. Is there any preference for, should I motivate the theorem or should I prove it first and then show you the application that we care about? Any advice on that, Dan, or others?
Yeah, I think it's probably just worth stating the theorem. I think many of the people here can have some idea what it might be useful for.
Cool, okay. Right, so theorem. This again comes directly pretty much from the work of Lin. So say we've got the function we're interested in calculating the RLCT of. And we can factor it like so. So through some other where this is also compact and semi-analytic. Ridiculous. And so on that, we will assume that, and so we'll be interested in a specific point, W hat in W, such that f of W hat equals 0. So that means that it possibly contributes to the asymptotics we're interested in. And then also assume that with U hat equal to U of W hat, the Hessian, which I'm going to write like this, the Hessian of G at U hat is positive definite. Then we'll define an ideal to be generated by each of the components of and the RLCTs will be equal. So right, and so we call this the fiber ideal because, yeah, it's just the fibers of the map U around, or no, the vanishing locus is related to the fibers. The reason we talk about regularly parametrized models, which is the title of the talk, is that if f and g are the Kale divergences of two different models associated to some truth on a parameter set, and g is associated to a regular model, then the Kale divergence around the true parameter will be positive definite. The Hessian, which is the Fisher information matrix, will indeed be positive definite, and so this is satisfied. And so the example, which I can sketch in more detail, that came up in my thesis is that if you if our map W is in fact just parameterizes probability distributions over some discrete set, then U might be the map into the simplex over Z, and in that case we'll win. This is satisfied, but I'll do that. Actually, write that down because that didn't make any sense. Right. So before we do that, I will prove the theorem over on the first of boards. Okay, so we will assume that you had because that doesn't really change anything. And so since is positive definite, we can find T linear. So H, which we'll define to be G composed with the inverse of T, from V equal to TU to R, and the form so all where and so all this is saying is that we're just changing the coordinates so that the Hessian of H is just all one. It's just the identity matrix, and so this is just an instance of the Morse lemma, I think. And then this expression that I've written down is just the Taylor expansion written in its own form. And so here, just because it'll be useful for us later, these are equal to T of the x's, where x is coordinates on U. That's confusing, I'm sorry, but I've already used the letter U for the function. Okay, so now we're going to shrink our... Oh, sorry, I didn't say this in the statement of the theorem, but it's actually only on a neighborhood of W hat that the equality holds. I'll state that more precisely when it comes up. Right, okay, so now we're going to shrink to some set V, subset of V, so that H tilde of V prime is bounded, so might as well say minus a half and a half. This is just by continuity. So then we can write that if we abbreviate this sum of squares as just V squared, that a half V squared is less than or equal to h of v is equal to 3 over 2 v squared for v in v prime. So this is already looking promising. We've sort of got some constants, but other than that, it seems like h is Lipschitz equivalent to a sum of squares. And so now we just want to extend that to all of, to the original coordinates x. So we can write v squared, as v transpose v. Yes. And so that equals, where x are our coordinates on v, times t transpose t. I'm going through this in detail because I sort of had to think about it for a surprisingly long time. And so we have, so t transpose t is symmetric, and so the eigenvalues are real and positive, I think, yes, or can be chosen to be. And so let lambda and mu be the smallest and largest eigenvalues of t transpose t. And so that will tell us that lambda x squared be less than or equal to b squared less than or equal to mu x squared. And so this implies we have lambda over 2 g of okay, but if we want to look at the function f, then we just compose with u, and so x is just equal to u of w. So xi equals ui w, and so x squared equals ui u1 w squared plus okay, and so because we assumed that ui hat was just the origin, this is exactly the function that calculates the RLCT of our fiber ideal. And so this is this inequality holds on v prime, or u prime. And so that tells us, I'll write it down precisely on the next board. So therefore on we have that RLCT w prime okay, just as a side note, I forgot about this business with shrinking the neighborhoods, because once you do the whole story with resolution of singularities, it doesn't really matter. So yeah, you can define for any given 0 a local RLCT, which is just on some neighborhood of that 0, and the global one is just the minimum over the local ones. And so yeah, kind of this bit on some neighborhood of where f vanishes is all you really need. Right, and so that proves our theorem that the RLCTs are related. So now I'll give an example if there are no questions on that so far.
Yeah, sounds good. It's a very useful trick. In some sense, the proof is not very hard, but
Yeah.
very useful to think about it as a composite this way.
Yeah, yeah. And so, well, I'll just give where it came up in my thesis, and so that's kind of why I care about it. And so, suppose, so we've talked a fair bit about these. We have some model, a truth, and a prior. And so we're going to assume the parameter space is compact, and also that the so Q is a probability distribution, but will be just over some finite set. And this is just the standard simplex over Z. Very clearly, my palm doesn't touch the whiteboard in the way that the rejection code likes. So this is just...
Sorry about that.
No, it's clearly, I'm joking. It's not your fault. And so that's just a formal sum where each xi and the sum of the xi equals 1. And so, yes, that's all I just mean by that, is it's just a probability distribution over some finite set. And so that means the map P of Z given W will be a map from W, our parameter space, into this probability simplex. Okay. And so, for example, in my case, if I were to be talking about program synthesis on Turing machines, Z might be the collection of tape letters, and if we're examining the output square of our Turing machine at some time, then P is just the smooth relaxation of the transition function of our Turing machine that tells us, given some distribution, which will be W in W, given some distribution over the input squares, what is the distribution of the output square. And so this extends to multiple squares or to the state or in whatever way you want to think about it. Right. So just going to erase the theorem off that board. So then K of W will be the KL divergence. This is confusing, I apologize. Of between Q and P of blank given W. So this is for any fixed W. Well, anyway, let's just write it down. So this in some sense is P. So this factors like that, dKl against some Q, where Q is just a point in that probability simplex. And so in the notation of the theorem, our U hat will just be the true distribution Q. That's the only place where the KL divergence in the sort of traditional sense vanishes, is if the two distributions are equal. And so, yeah, that's the point in question. And so all of the singularness, potentially, is wrapped up in the function P. Yeah, and so it turns out that the KL divergence of where it's just the map from the probability simplex to R is indeed regular around the point Q, and so the theorem applies, and the fiber ideal in this case is I is generated by P of Z given W minus Q of Z for Z in Z. So this is just, these are where we will assume some analytic function of the parameter W here, and there will usually be some perturbation away from the boundary, but that kind of doesn't enter into it exactly. And so this has kind of a nice conceptual content, right? So this ideal is just generated by the difference in the probability that our model assigns to some element of the set we're interested in, minus the difference between that and the probability that the true distribution applies to it. So at least to me, this makes a lot more sort of like intuitive sense than the, well, K of W equals sum of, I'll skip the perturbation for the moment, you just assume it's all on the interior. And so it turns out that this ideal and this function K have the same RLCT on W, at least again in the neighborhood of a true parameter. Yeah, and so quite apart from that, making the calculation significantly easier. So in the example of Turing machines, this P is just a polynomial, whereas this has logs and all the rest of it in it. It also feels like you're associating a more geometric notion to these models. And so if you have differing models, say by adding or removing constraints, they're related by simple operations on the ideals and so on and so forth. Okay, that's probably a good time to pause for any questions. If no one has any objections, I'm also more than happy to talk about some of the nice properties of the RLCT of an ideal, but that's kind of the main content of the talk, I would say.
Doesn't seem like there's any questions right now. Yeah, I think you can go on with any of those things. Remind me what are the limits of using this regular parametrization? And I remember there was something we were trying to do with it that we actually in the end couldn't do with this technique, but sorry for the vague question, but I can't remember what it was.
No, that's fine. And so where we lost out is that we assumed that Z is finite.
Right.
And so that corresponded to applying finitely many constraints to our Turing machine. And so that's interesting because by the Hilbert basis theorem, even if we apply infinite many constraints, this ideal is still finitely generated. And so finitely many of the constraints suffice, but you don't, in that case, you only have one inequality on the RLCTs. Even though the ideal is kind of still well defined, you can still associate an RLCT to it, but it doesn't necessarily match that of the KL divergence.
Right.
Which is, I don't know, felt bizarre, but also is probably more deep than the finite case, as Spencer's talk will attest to. Is that what you were thinking of?
Yeah, that was one of the things. I also remember so the fiber ideal is defined point by point in, I don't know what the notation is, in delta Z or is it in W?
In W is what the theorem was getting at. And so yeah, the RLCTs match on some neighborhood at that point, but somehow because there's only one, because the model G in the notation of the theorem is identifiable, there's only kind of one fiber ideal.
Right.
At least in the regularly parametrized case.
Yeah, I guess at some point we were considering whether this result of Lin's could make it easier to do the kind of thing that Spencer's doing, where you try and find a global polynomial that's comparable.
Yeah, sure.
It's not. It seems like you sort of need to know. I mean, exponential models are regularly parameterized, so in principle you could apply these techniques to neural networks, I think.
Yeah.
But then the question is, can you identify the fiber ideal and its generators? Maybe that's the issue.
Yeah, I think that is also complicated because this only is a simplification insofar that P is simple, whereas in a neural network, that would be the actual function that the neural network computes, right?
Mm-hmm.
And so that's not necessarily like much better than that function, but with logs.
Right. Yeah, that's true.
I think is part of the issue.
Mm-hmm. Yeah.
Okay, well, there's about 10 minutes, and so, I mean, obviously, as usual, no obligation to stick around and listen to me wrap it on, but I might just write down a couple of nice properties of these RLCTs because, I don't know, it's kind of appealing.
Yeah, I think these identities are well worth knowing and not at all obvious from the KL divergence formulas, as you pointed out.
Yeah, and so we'll just work as before with, so I and J might be ideals in the ring of analytic functions with W as usual. And we'll just fix some prior throughout. And so we've seen that if I is a subset of J, then will be less than, let's say, J associated to a given prior. And so that's just, well, we did it by actually writing the generators of I in terms of J, but you can also just add some generators to extend the ideal I to J, and you will kind of more obviously have the inequality between, so say I equals, will be a subset of J, but that's just the same as if you just add in all the F's. Which is the lazy way of proving the same result. also, if you have an integer which is positive, then, and the RLCT of some ideal is, then you can compute any power of that ideal. We'll just need lambda over r theta. And so this just works by comparing the generators of the powers with just with that function. So the sum of squares of the generators, and it ends up pretty straightforward. There are nodes. And so that's kind of useful because, so define for an ideal and a point. Yeah, so for P and W, the order at P of your ideal equals K, where K is the supremum over N, such that this is not helpful. Such that the ideal I is contained in the maximal ideal, the power of that number N. And so for a function, this is just your usual order of vanishing. Then we can calculate the RLCT of this by in some neighborhood of the point P of MP. And we'll just, use a constant prior. In this case, is going to be it's a terrible letter like that. R. So N is the dimension over 2R, and then 1 will be our multiplicity. And so will be less than or equal to 2 times the order at P of I, 1 for all P in the vanishing locus. So this is just kind of a coarser invariant, the order, than the RLCT, but this proves that they're kind of related in an appealing way. So one way to think about the RLCT is it's measuring how singular, so how flat your function or ideal is around the points where it vanishes. And so the order just is a coarse measure of that, and so this proves that the RLCT kind of subsumes this easier, this sort of coarser invariant. So the last results I will state on the other lot of boards are for sums and products of ideals, which is also very useful. So let's say we have W1 and W2 are semi-analytic. And we have some ideals in their respective rings of analytic functions and set W to be W1 Cartesian product W2. Consider just by composing with the projections so any analytic function on the Wi is just an analytic function on W. And so settings with some prior on each one, then we have the formulae. So we can take the sum of the ideals and you just get, oh, this I wanted to set. Will just gives you the sum of the lambdas. And for the product, and so you can demonstrate the first one by looking at the partition functions, and the second one by looking at the zeta functions. Sorry, I've been using partition function all the way through. Laplace integral is usually the term that actually gets used, but it's the same thing. So just before I let you all go, we've assumed that these are kind of somehow separate ideals. They're on disjoint parameter spaces. It would be very, very nice if we could prove that for any ideals, we have this same thing, but with an inequality. And so that's not clear at the moment. It's true for complex log canonical thresholds. But yeah, anyway, unclear in the real case and probably deeper than what we've been getting at so far. Anyway, that's all from me. Thank you very much for coming, and let me know if you have any questions.
Thanks, Tom.
Thank you.
Yeah, thanks. Is that related to the adjunction of inversion?
Yeah, I think that's what they call the inversion of a junction, something like that.
Oh, right. Yep. Other way around.
Yeah. Close enough. Let me double check if that's actually the same statement. But yes, that's basically what I'm getting at. I saw some notes somewhere about jet schemes. Was that you trying to?
Yeah, that's right. I'm heading in the direction of trying to understand that that theorem. It's very interesting.
Cool.
Yeah.
Yeah, so the inversion of a junction is the statement that if you have, so in the case of varieties, if you're doing this, if you have y embedding in x a non-singular closed subvariety, and I is our ideal. Though this is all in the complex case, so we call it and then the inversion of a junction is that LCT at P of is less than or equal to the log canonical threshold of the original for P and Y. Yeah, so things get more singular if you restrict them to a subvariety. It's the thrust of that, which lets you prove the statement I gave before about sums.
Right.
Yeah.
Yeah, just at a high level, so the connection to jet schemes is there are lots of things you can do to a singular variety or singular scheme to pull it apart at the singularities. One is to resolve it by blow-ups. There's many different forms of blow-up. So there's the sort of ordinary one, there's the Nash blow-up, there's various other kinds of things, but they all have the flavor of replacing a point by the data of a point and some sort of trajectory or plane or other geometric datum through the point.
Yeah, sure.
Jet schemes do that with something called arcs. And one of the difficulties in really making use of singular learning theory is how deeply embedded the resolution process is, right? And it's very difficult to do resolutions. But a lot of these results on RLCTs make use of something that's, I mean, the jet scheme is in some sense a more tame object than the resolution. So you define it all in one go. It's not an inductive construction like the resolution. So yeah, one of the more promising routes of making use of more geometry and singular learning theory is to try and see how much we can do with the jet scheme rather than the resolution, I think.
Right. Yeah, okay, that makes sense.
And yeah, I guess I would. So when Nash introduced the jet scheme, that was kind of that's the role it's kind of played in geometry, I think. I'm not an expert, but at a high level, that seems kind of accurate. So yeah, one could hope that a similar strategy might work here. Anyway, that's an idea.
No, that sounds very cool. Right, I will let everyone get to their tea break. But
yeah, thanks very much, Tom.
Thank you.
Thanks again, Tom.
Thanks, Tom.
Oh, maybe there are other questions. I don't know.
Yeah.
I kind of hogged to that.
No, speak up if there are.
Okay, maybe not.
Okay.
All right.
Thanks, Dan.
Yeah, thanks again.
Dan,
Okay, so we got it. Yeah. Let's find somewhere to chat.
Cool.
So I'm going to go off with Matt and chat to him for a minute, and then we have half an hour, and then we're starting the working session. So I'll see you all back then, hopefully.
Lead the way.
Sit over here.